Hi everyone, my name is Angus and I'm a PhD candidate at the Autonomous Systems and Biomechatronics Lab at the University of Toronto in Canada. I will be presenting my paper entitled Robots Autonomously Detecting People, a Multimodal Deep Contrastive Learning Method Robust to Intraclass Variations at IROS 2023 in Detroit. Currently, robots in human-centered environments need to be able to detect people in order to engage in effective human-robot interactions. For example, in grocery stores, robots can be used to locate customers and guide them to specific products. In long-term care homes to assist in daily activities. In hospitals to provide directional guidance to staff, patients, or visitors. And in urban search and rescue scenarios to search for victims. However, human-centered environments are typically crowded with people or cluttered with objects, leading to frequent occlusions of individuals. These environments typically also have variable illumination due to natural and artificial lighting sources. Lastly, the articulated nature of the human body, combined with a wide variety of clothing, introduces high level of deformation, further complicating the detection problem. These types of challenges are collectively known as intraclass variations. Therefore, the goal of this research is to develop a deep learning person detection architecture for mobile robots in human-centered environments which is robust under intraclass variations. We present a two-stage person detection architecture for mobile robots that consists of a unique pretraining method which we call TimCLR and a multimodal YOLOv4 detector for fine-tuning. The research contributions are thus the development of a new pretraining method, TimCLR, that pretrains the detector using contrastive learning. TimCLR uniquely incorporates intraclass variations by generating multimodal image frames from sampling videos within a short temporal interval. We uniquely incorporate contrastive learning within a fusion backbone to contrast multimodal image features to capture crossmodal invariances. Our architecture diagram consists of two training stages and an inference stage. We first pretrain our detector using our TimCLR method on a large unlabeled dataset. Once this is done, we transfer the model to the second stage. In the second stage, we fine-tune the detector using a smaller labeled dataset with our MYOLO detector. Once trained, if we want to make a prediction, we can discard the first stage and pass in images directly into the MYOLO detector, which outputs person and body part bounding boxes. Contrastive learning is an unsupervised learning framework which learns through pairs of images. The dataset is organized into positive pairs and negative pairs. The network is trained to maximize the feature similarity between positive pairs and vice versa. To generate pairs of images which differ only in intraclass variations, we use video sequences which naturally capture variations in person appearances. For example, from frame to frame, people may change poses, lighting may change, and people may become occluded. The idea is to use different frames within the same video as positive pairs. For example, any of these two frames, because they occur within a short time interval, roughly captures the same scene but under two different sets of variations. The goal is to train a network that extracts the same features for each of these images. This results in the network being able to learn and extract invariant features. For pretraining, we use the NTU RGB-D dataset, which contains multiple dynamic people performing different actions such as standing or jumping. For fine-tuning and evaluation, we use three different datasets with varying levels of person occlusion, illumination, and deformation. All of these datasets were collected from real-world environments by a mobile robot with a Kinect camera. The mobility aids dataset was taken from a crowded hospital environment and provided a good source of person occlusions. The USAR dataset contains multiple static people and body parts in cluttered environment. This dataset provides a good source of occluded people and body parts, pose deformation in different lighting conditions. The IOD dataset contains multiple dynamic people in indoor and outdoor campus environments. This dataset provided a lot of examples of varying lighting. Here are visualizations of the detection results on all three datasets, with each row corresponding to a different dataset. The first column corresponds to our method, and the second and third columns correspond to the baseline methods. In each case, our method was the most accurate in identifying all people and body parts under all different conditions. Lastly, I look forward to meeting you at IROS, where my presentation will go into further details regarding the state-of-the-art in person detection, details of the proposed methodology and architecture, and experimental results in comparison of our novel method. Thank you.